Section 6.2, Logarithmic Functions and their Graphs. So our goals for this section are to determine, what is a logarithm, how to convert between exponential and logarithmic forms of equations, how to evaluate logarithms, how to treat the logarithm as an inverse of a certain function, sketching logarithmic functions, and some applications. So first, what is a logarithm? A logarithm is a different way of expressing an exponential relationship, where, in one way of thinking, the input is a number and the output is the exponent to which a base must be raised to yield the input. So a question that we might ask along this line would be, what exponent goes on base 2 to yield 32? Well, I know that 2 raised to the 5th power is 32. So what we would say is the logarithm base 2 of 32 is 5. All right, the exponent that goes on base 2 to yield 32 is 5. All right, so a logarithm is an exponent that goes on the base to yield some number. All right, so a general definition of logarithms. Let b be positive and not equal to 1. An exponential form, x equals b to the y. This is true if and only if the log base b of x is y. The logarithm base b of x is y. So notice in both of these forms, the base is the same number, right? The base on the exponential is the same as the base on the logarithm. And this is true for x positive and every real number y. All right, so logarithms are only defined for positive values of the input. X must be positive. We read that expression, log base b of x, as the logarithm base b of x. So this phrase, the logarithm base b of x is y. We need to be able to convert between exponential and logarithmic forms of an equation. So let's see some examples of that. We're asked to write the following exponential equations in logarithmic form. We are told that 6 to the negative third is 1 over 216. So then I can write this in logarithmic form as the log base 6 of 1 over 216 is negative 3. All right, 6 to the what power gives us 1 over 216? Now the second example, the cube root of z equals m, well, that doesn't look like an exponential equation. But recall that the cube root of a number is the same as raising the number to the 1/3 power. So I can write the cube root of z equals m as z to the 1/3 equals m. Then in logarithmic form, the log base z of m is 1/3. Now let's go in the other direction. Write the following logarithmic equations in exponential form. The log base 9 of 3 is 1/2. So what this tells me is the exponent that goes on base 9 to get 3 is 1/2. The exponent that goes on base 9 to yield 3 is 1/2. You might say, well, how does that make sense? Why is 9 to the 1/2 3? Well, the 1/2 power is the same as the square root of 9, and the square root of 9 is 3, so this statement does make sense. The log base a of 12 is r. So the exponent that goes on base A to yield 12 is r. A to the r is 12. All right, so let's evaluate some basic logarithms. The log base 3 of 9. All right, so the log base 3 of 9 is some number. Oops, not 9, sorry. The log base 3 of 9 is some number. Now remember, what does this say? This says the exponent that goes on base 3 to yield 9 is what? 2. The log base 3 of 9 is 2. Let's look at the example to its right. The log base 3 of 1/9. Alright, so the exponent that goes on base 3 to yield 1/9 is what? Alright, so now you have to remember some rules for exponents here. If 3 to the second is 9, 3 to the negative second is 1/9, so the log base 3 of 1/9 is -2. Alright, remember in general, your rules for exponents. A to the negative nth power is 1 over a to the nth. So 3 to the negative second is 1 over 3 to the second, 1/9. The log base 5 of 1 is what number? So then 5, the exponent that goes on 5 to yield 1 is 0. Any non-zero number to the 0 power is 1. The log base 5 of 5. 5, the exponent that goes on base 5 to yield 5 is 1. The log base 3 of 9, the log base 9 of 3. The exponent that goes on base 9 to yield 3. 9 to the what power equals 3? Well, now we have to be a little tricky. I know that the square root of 9 is 3. So I have to remember that property of exponents, that in general, a to the 1 over nth power is equal to the nth root of a. Right, so you have to remember all these rules for exponents when dealing with logarithms. 1/2. 9 to the 1/2 power is the same as the square root of 9, which is 3. Log base 16 of 1/2. 16, the exponent on base 16 to yield 1/2 is what? Alright, so now let's see. 16, I know it's going to be a negative. I know it's going to be a negative because if it was a positive value, I wouldn't get a half, I would get a whole number. Alright, so let's see. I know that the fourth root of 16 is 2, because 2 to the fourth is 16. So then the fourth root of 16 is 2, so then I have 1 over the fourth root of 16 would be 1/2. So that's the same as 16 to the negative 1/4 power. So then the log base 16 of 1/2 is negative 1/4. Alright, the common logarithm. The logarithm with base 10 is frequently used and has a special abbreviation. In general, we don't write log base 10 of x. We simply write log x. And the base 10 is understood. Alright, so then the log of 10,000. The log of 10,000 asks us, understood, base 10. What exponent goes on base 10 to get 10,000? Well, since it's a 1 with just a number of zeros after it, you just read the number of zeros. So that would be 4. The log of 1 over 100. 10, right? to the what power gives us 1 over 100. Well, 10 to the second is 100, so the log of 1 over 100 is -2. The log of 10. 10 to the what power yields 10. Log of 10 is 1. Log of 750. 10 raised to the what power gives us 750. Well, that's tough. I know it's more than 2 because 10 to the second is 100, but less than 3 because 10 to the third is 1,000. But other than that, I'm not sure. Alright, so notice on your calculator there is a log button over on the left-hand side. And if we use this log button, it is the base 10 logarithm. It is the common logarithm. So the log, for example, the log of 10,000, our first example on this slide, we hit enter and we do get 4. And the log of 1 over 100 is -2. Alright, so the log of 750 is 2.8751. Let's take it to 4 decimal places. And it is an approximation. Alright, this is an irrational number, and it will continue on forever. The decimal number will never repeat. Right, so we do have that button on our calculator for the base 10 logarithm. Alright, since the basic exponential function f of x equals b to the x, with b positive and not equal to 1, is 1 to 1. Alright, so let's think about that. It's a 1 to 1 function. B to the x, remember, if b is positive and b is not equal to 1, let's assume that, let's just take one example where b is, let's take the example where b is greater than 1. Remember that we got this graph that did something like this. And it is a 1 to 1 function, right? Horizontal line test says this is a 1 to 1 function. So therefore it has an inverse that is also a function. Alright, so if f of x is b to the x, determine its inverse. Alright, so, well, y is equal to b to the x. Let's first write it as y equals b to the x. Then invert the variables. And now we have this. Well, let's write this. Let's turn this over. Since we need to get the y by itself, let's write this in a logarithmic form. So I could write this, the log base b. Okay, to yield x is y. So if f of x is b to the x, then its inverse function is the log base b of x. Alright, so every basic exponential function has a inverse that is the logarithmic function with that same base. Now remember that for the basic exponential function, we had domain of -infinity to infinity and range of 0 to infinity. Well, now for the inverse function, recall that when we have an inverse function, we invert the domain and range. So for the inverse function, the log base b of x, the domain of the inverse function would be 0 to infinity, and the range would be -infinity to infinity. Alright, so in general, if we let x be a positive number, let b be positive and not 1, the inverse function of f of x equals b to the x is called the logarithmic function with base b, and is denoted by f of x is the log base b of x. The domain of f of x is the log base b of x is a set of all positive numbers, or 0 to infinity. The range of f of x equals the log base b of x is a set of all real numbers, -infinity to infinity. Alright, so for example, if f of x is 3 to the x, determine the inverse function, and let's call it g of x. Well, if the base is 3, we could go through that whole process again to find the inverse function, or we could just remember what we just did. Then g of x, the inverse function, would be the log base 3 of x. Evaluate f of 4. F of 4 would be 3 to the 4th, so then f of 4 would be 81. G of 81 would be the log base 3 of 81. 3 to the what power yields 81? G of 81 equals 4. And so notice that there's that inverse property. F of 4 is 81, G of 81 is 4. So this is one example that demonstrates that it's reasonable that they are inverses. Sketch f of x is the log base 3 of x. So what I'm going to do here is I'm going to start with the inverse function. I'm going to start with the exponential function 3 to the x. Alright, so let's start with, I'll call it g of x. And let's x and 3 to the x. So let's just do a few points here. How about -2, -1, 0, 1, and 2? Then I would have what? 1, 3, and 9, 1/3, 1/9. Now, for my function, x and f of x, all I have to do is invert the variables. 1/9, -2, 1/3, -1, 1, 0, 3, 1, 9, 2. Alright, plotting the points. 1/9, let's just use a scale of 1s on each axis. 1/9, -2, so it'll be about here. 1/3, -1. 1, 0, 3, 1. Oops, I plotted 2, 1. Should be 3, 1. And 9, 2. Now, remember that the domain, right, the domain of this function is 0 to infinity. And in fact, there will be a vertical asymptote for the curve at x equals 0. And if you remember that the exponential function had a horizontal asymptote at y equals 0, it should make sense that we have a vertical asymptote on this curve at x equals 0. Alright, so let's draw the curve. It's asymptotic, increasing rapidly, and then changes to a very slow increase. Alright, so there's the sketch of f of x equals the log base 3 of x. Now what if we wanted to sketch f of x is the log base 1/3 of x? Well, again, I could start with the inverse, x and 1/3 to the x. And, if you remember, this was just a horizontal flip of the exponential function. And so then, for x and f of x, I would invert the variables. 9, -2, 3, -1, 0, oh, that shouldn't be 0, 0. That should be 0, 1. Sorry about that. So then I should have 1, 0 here. 1, 0, 1/3, 1, 1/9, 2. Alright, and I'll plot the points, in a sense, from bottom to top here. Again, using a scale of 1, 1/9, 2, 1/3, 1, 1, 0, 3, -1, 9, -2. And so if you look at this graph, it appears to be basically the same graph, but a vertical flip of the graph. And it is a vertical flip of the graph. We again have the asymptotic feature with rapid decrease and then very slow decrease as we move on. Right? And again, we have an asymptotic feature at x equals 0. So we have a vertical asymptote at x equals 0. Alright, so in general, if we want to graph the logarithmic function, the basic logarithmic function, f of x is the log base b of x, where b is positive and not equal to 1. Right? We don't want the base to be 1. The domain will always be 0, infinity. The range will always be negative infinity, infinity. The x-intercept of the basic logarithmic function will always be 1, 0. The y-axis will always be the vertical asymptote. Remember, that can be denoted by the equation x equals 0. The function is 1 to 1, and the function will always pass through the point b, comma 1. Right? We saw, the log base 3 of x, right? When we had the log base 3 of x for our function, remember that f of 3 was 1. Right? When the input was 3, the output was 1. If we have base greater than 1, right? So if the base is greater than 1, we get the increasing function. If the base is between 0 and 1, we get a decreasing function. Alright, so now how would we sketch the log base 3 of x plus 2 plus 4? It's just a transformation of the basic function. The x plus 2 tells us to shift the curve left 2. The plus 4 tells us to shift the curve up 4. So for our log base 3 of x, we had the points 1/9, negative 2, 1/3, negative 1, 1, 0, 3, 1, and 9, 2. I need to shift the x's left 2. So let me subtract 2 from all of these. 1/9 subtract 2. That's what? Negative 1 and 8/9. 1/3 subtract 2. That's negative 1 and 2/3. Negative 1. 3 subtract 2 is 1. 9 subtract 2 is 7. Alright, let me shift this up 4. So I'll take the outputs and shift it up 4. That will give me 2, 3, 4, 5, and 6. Now, what about my vertical asymptote? Well, my vertical asymptote will also shift left 2. So there's my vertical asymptote at x equals negative 2. And now I'll plot the points. Negative 1 and 8/9, comma 2. Negative 1 and 2/3, 3. Negative 1, 4. 1, 5. And 7. 1, 2, 3, 4, 5, 6, 7. 6. 1, 2, 3, 4, 5, 6. We still have the asymptotic feature. And increasing. So there's the sketch of the log base 3 of x plus 2 plus 4. Alright, the log base 3 of the opposite of x minus 5. Alright, so let's remember, what does the opposite of x do? Alright, that gives us a horizontal flip. And then down 5. Alright, still the log base 3. So a horizontal flip. Alright, if we again start with our basic x versus log base 3 of x, those same points that we've been using. So 1/9, 1/3, 1, 3, and 9. And negative 2, negative 1, 0, 1, and 2. Horizontal flip. I need to change all of the signs. So let's throw negatives on all of these. Shift it down 5. Alright, so that would give me what? A -7, -6, -5, -4, and -3. Alright, let's plot these new points. -1/9, -7. 1, 2, 3, 4, 5, 6, 7. -1/3, -6. -1, -5, -3, -4, and -9, -3. Alright, so let's see. As this curve moves from left to right, what's happening here? The curve is decreasing and then becomes asymptotic. Right, we do have that vertical asymptote still at x equals 0. So notice how this is basically a vertical flip. I'm sorry, a horizontal flip of the standard curve. Determine the domain of each function algebraically. Alright, so recall that for our basic function, the domain, if we had just f of x is the log base b of x, we said that the domain was 0 to infinity, which is the same as x is greater than 0. So what that means is our argument for the function, this part right here, must be greater than 0. So now we have f of x is equal to the log base 7 of 2x minus 9 plus 5. What's important is the argument of the function, the 2x minus 9, must be greater than 0. We solve this inequality by adding 9 and dividing by 2. So therefore the domain, x is greater than 9/2, would be 9/2, comma, infinity. G of x is the log of 12 minus 3x. And remember, that means that that's the log base 10. Right, but what's important, the argument must, to determine the domain, the argument must be greater than 0. 12 minus 3x must be greater than 0. Subtracting 12, negative 3x is greater than negative 12. Dividing by negative 3, x is less than 4. Remember, when you divide or multiply an inequality by a negative number, you must invert the symbol. So the domain of this function is negative infinity to 4, parenthesis. So now let's take a look at a couple of applications of logarithms. One application is the Richter scale, and that's a way to express the magnitude of an earthquake. And it's given by the formula r is equal to the log of I over I sub 0, where I and I sub 0 represent the intensity of the current earthquake and the intensity of a standard reference earthquake. Alright, so now that I0 is a certain measurement, a certain intensity, and is given by 10 to the negative 4th centimeters. The world's strongest recorded earthquake had a magnitude of 9.5 on the Richter scale. Calculate the earthquake's intensity in terms of I sub 0. The magnitude was 9.5. So that's the Richter number, that's the R value. So we know that 9.5 is equal to the log of I over I sub 0. Now, since we're asked to calculate the earthquake's intensity in terms of I sub 0, I'm not going to replace that I sub 0 with 10 to the negative 4th. I'm going to leave it alone. And I need to solve for I. I need to solve for I. So the first thing that I'm going to do is I'm going to remove the logarithm by expressing this in an exponential form. Recall that the understood base, since this is a common logarithm, the understood base is 10. So then, writing this in exponential form, I have 10 to the 9.5 is equal to I over I sub 0. Now to solve for I, all I need to do is multiply both sides by I sub 0. So 10 to the 9.5 I sub 0 is equal to I. So now calculate the earthquake's intensity in terms of I sub 0. What is 10 to the 9.5? What does that mean? 10 raised to the 9.5 power. Wow, that's a big number. What is that? Hundreds, millions. Let's see, that would be thousands, millions. So that's 3.16 billion. All right, so conclusion. The intensity was about 3.16 billion times the intensity of the standard reference earthquake. All right. With this Richter number, every time you move up 1 on the Richter number, the intensity increases by 10. So we're moving up, in a sense, 10 on the Richter number, from 0 to 9, and so our intensity is going up by 10 to the 9th power, so we're in the billions. The decibel scale is another example of a scale that's based on a logarithmic expression. The decibel scale is given by the formula d is equal to 10 times the log of I over I sub 0, where I represents the actual intensity of the sound in watts per square meters, and I sub 0 represents the intensity of the faintest audible sound that a person can hear. So I sub 0 in this is 10 to the negative 12th watts per square meter. And just as a note, a decibel level greater than 85 is considered unhealthy. Alright, so here's an example. The sound intensity of a jet taking off from a distance of approximately 165 feet is 100 watts per square meter. Find the decibel level. Alright, so then the decibel level would be equal to 10 times the log of, now let's see, I represents the actual intensity of the sound. The intensity of the sound here is 100 watts per square meters. So 100 over I sub 0. So that would be 10 to the negative 12th. Alright, so let's see. Now notice that that's 100 is 10 to the second. So we have 10 to the second over 10 to the negative 12th. And if you remember your rules for exponents, that will be the log of 10 to the 14th. Alright, because 2 minus negative 12 is 14. Now wait a second, what's the log of 10 to the 14th? Remember that that's a base 10. So 10 to the what power yields 10 to the 14th? Well, it's got to be 14. And so that's 10 times 14, which is 140. So it shouldn't seem surprising that if you're not too far away from a jet engine, it's pretty loud. All right. So the decibel level is 140 decibels, which would be considered unhealthy. And that's why people who work near jet engines often wear, earmuffs, right, so that they don't damage their ears. One more application, the pH scale. The pH scale measures the acidity or alkalinity of a solution, and is given by pH is equal to negative log of H plus, where H plus is the hydrogen ion concentration measured in moles of hydrogen ion per liter. This scale measures from 0 to 14, with 0 being highly acidic, 7 being neutral, and 14 being highly basic. So for example, Coca-Cola Classic has a pH of about 2.5. Determine its hydrogen ion concentration. Well, the pH is 2.5, so then we have 2.5 is equal to negative log of the hydrogen ion concentration. Let's solve for H plus to determine the hydrogen ion concentration. Let's divide through by the negative 1. Negative 2.5 is equal to the log H plus. Our understood base here is 10. Converting this to an exponential form, I would have 10 to the negative 2.5 is equal to H plus. And using a calculator, notice that the second function of the log key brings up 10 to the power. So negative 2.5 is 0.003162. Alright, so conclusion, the hydrogen ion concentration for Coca-Cola Classic is 0.003162. What are the units on that? Moles per liter. Alright, that concludes the presentation for this section.